Hello everyone, I'm Emmanuel Biabiani from the University of the French West Indies. In this video, I'm going to give you a short presentation of the work we presented at Joint Conference CAP and RFEAP 2020 concerning the use of an expert deviation carrying the knowledge of climate data in usual algorithms. In this work, we use spatio-temporal data giving a numerical view of meteorological situation in Lesser Antilles. Wind speed intensity and cumulative rainfall measured by satellite are used. These are the main parameters that influence the climate dynamic in this region. Usual clustering algorithms do not provide relevant results according to atmospheric physicists. In all the previous work, the quality of the cluster is used to be evaluated by visual interpretation. So, our main objective is to improve the clustering of complex spatio-temporal data, such as meteorological parameters. So we therefore need to understand why the clustering results are so poor. In this abstract, we focus on improving the dissimilarity measure used in clustering process. In order to get more relevant results, we try to include knowledge into clustering process. And a numerical assessment of the cluster covariance is provided by silhouette index. L2 norm is commonly used in clustering algorithm, but its high sensitivity to spatial variation make it a weakness when dealing with meteorological fields such as precipitation. For example, from a reference, a field with a high and localized fluctuation is similar to a field with distributed fluctuations, and a field with a small shift is similar to a field with a large one. To design a better dissimilarity measure, we were inspired by an image processing method. We subdivide each daily field into several patches corresponding to the location of the specific atmospheric structures identified by experts or from scientific literature. Each patch, each piece of matrix, is transformed to histogram by using the scintille of ground station records as edges of the histograms bins. The Kullback Leibler symmetrized divisions are used to compare histograms of fields. The average of all histograms provides a new dissimilarity measure called Expert Deviation. The silhouette index allows us to compare clustering algorithms results and shows the number of clusters. The new metric produces better results than L2 norm, especially when it is integrated in K-means algorithm. Typically, when silhouette index is higher than 0.2, this reflects the presence of well-defined structures in the dataset. The results are pretty similar for more continuous fields such as wind. To ensure that those clear numerical results correspond to real improvement from the physical point of view, we studied intensively the resulting clusters. Here, for the sake of consciousness, we only represent the intra-annual dynamic of the resulting clusters. KMS-ED clusters are more realistic than L2 ones. For KMS-L2, excepted C1, the other clusters are quasi-similar. KMS-ED provide clusters with pretty different patterns. That is not the case of KMS-L2. There is a real interest in adapting the classic methods of clustering to handle complex data. The results of the silhouette index are more relevant from the physical point of view. Using an expert distance consistently produces better results than L2. The perspectives of this work are multiple. For example, we could design expert deviations for each meteorological parameter characterizing the climate. This will allow us to combine these expert deviations in clustering using several meteorological parameters to provide a complete analysis of the climate. Another approach consists in performing a clustering with the first parameters and then analyzing the impact of these resulting clusters in another parameter. Thanks for watching.